Now this question is related to the chapter on alcohols and carboxylic acids or organic chemistry in general. This question talks about vegetable oil. In the question, we are given some key pieces of information on vegetable oil. Firstly, vegetable oils are triesters. They react with methanol, and the reaction uses a potassium hydroxide catalyst. And in the question, they actually show you the reaction equation between vegetable oil and methanol to produce something called biodiesel. So for part A, it's a giveaway. You are asked to explain why is vegetable oil a triester. So from the name, in naming of covalent substances, we have learned that tri means 3. Okay, and then esters, we have learned in organic chemistry, it means that it belongs to a particular functional group. It belongs to a particular homologous series with a unique functional group. So in vegetable oil, naturally you will want to look for the ester functional group. Okay, so we can see that vegetable oil contains 3 ester functional groups, so that's why it's called a triester. In the subsequent question, you are asked to draw the structure of biodiesel molecule. This is where students tend to have issues with. Now, in the question, they actually tell you that biodiesel is also an ester. Okay, so you need to take note of that biodiesel is an ester. But then, have we learned the reaction between an ester and alcohol? The answer is no. So we need to first figure out what is happening in this reaction. Okay, a key clue that you have would be the other product other than biodiesel. So if you look at the other product, you find that you have this part. This is called a triol. All right, this triol. Firstly, you need to find out, look at the vegetable oil, which part of vegetable oil do you think this came from? Okay, I hope you all can see that it actually came from this part. Okay, and from vegetable oil, how do we end up with a triol? You have to recall that the esterification process is reversible. So after an ester is formed, it can also go back to forming the alcohol and the carboxylic acid in a reaction which we call hydrolysis. So from the triol product, we can actually guess that the vegetable oil must have undergone hydrolysis. And remember, how do we get back the acid and the alcohol? Is to break the CO single bond in the ester functional group. Okay, that will give us the triol. That would also give us 3 carboxylic acid molecules that looks like this. Okay, so there will be 3 of them. Now, is this already your biodiesel? The answer is no, because like as mentioned, biodiesel is also an ester. So this acid must go on to react with something to become an ester. So now we need to look at what is the other reactant in this reaction scheme. We can see that there is an alcohol, right? There's methanol. So from there we can tell that the acid that we have obtained from the hydrolysis of the vegetable oil must have reacted with this alcohol to form an ester, which is your biodiesel. So once again, given an alcohol and a carboxylic acid, how do we get the structure of the ester? The trick is to arrange the functional groups to face each other. So make sure that your alcohol functional group is facing your carboxylic acid functional group. And then how do we go on to get the ester? Is as follows. We need to remove the OH from your acid, and we need to remove the H from your alcohol, and then we combine the 2 remaining fragments together. So this is the structure of the resulting ester. This is also the structure of your biodiesel. So earlier I mentioned that the question stated that biodiesel is an ester. Where do you find it? You find it over here. Biodiesel is an ester. So when reading questions like this, you need to be very, very careful. Otherwise, you may think that biodiesel is the carboxylic acid fragment that is obtained from the hydrolysis of your vegetable oil. For part C, there is some new information about your vegetable oil which contains some impurities in the form of acids, and these acids must be removed by neutralizing them with an alkali before the reaction. So they go on to ask how and why using untreated oil will affect the rate of the reaction. So again, this question, there are two key points to be answered. How is your rate of reaction is going to be affected, and why is it going to be affected in this manner? All right, so since we are talking about rate of reaction, is related to the topic on speed of reaction. So in speed of reaction, we learn a few factors that affects the speed of reaction: concentration, pressure, temperature, particle size, and catalyst. So if you examine these five factors, which one would be more relevant over here? Okay, you may be tempted to think of concentration, but in the earlier part, they already mentioned that you use a catalyst. Okay, and catalysts are usually added to increase the speed of the reaction. And if you can recall, the catalyst that's being used is potassium hydroxide. So what happens if your vegetable oils contain acids, impurities? Obviously, your acid is going to react with your potassium hydroxide, which is your catalyst. And what happens when your catalyst is reacted away? That means you have no more catalyst. Then the rate of reaction will decrease because your acid reacts with potassium hydroxide, which is a catalyst for the reaction. So part D follows from part C, which we mentioned that there are some impurity acids that must be reacted away. So in part D, they are talking about reacting the acids in oil, in vegetable oil, with potassium hydroxide in a titration. So what we have is that 10 grams of oil is titrated with potassium hydroxide. The concentration is 1 gram per dm cube, and the volume of potassium hydroxide required is shown in the titration table. So this requires you to recall in a titration. Once you reach the end point and you get the titer value, we can actually make use of the titer value to find out the amount of the reactant in your original sample. So we want to find out the amount of acid that's present in 10 grams of oil. Next, when we look at the titration results, you will find that there's a rough titration where the value is very much different from the other two. Remember, in titrations, we only use the consistent results or your best titration results. In this case, would be the titer values of titration 1 and 2. So the average volume of potassium hydroxide required to neutralize the acids would be 21.55 centimeter cube. Now from there, this is a bit different from our usual 3C approach where we convert to moles. If you look at the question, they want you to calculate the mass of potassium hydroxide needed to neutralize the acid in 1 kilogram of oil. Okay, so firstly, they want to find the mass of potassium hydroxide. Now this is rather straightforward because the concentration is given as grams per dm cube, meaning the mass over volume. All right, so we can easily find the mass of potassium hydroxide by taking the volume multiplied by the concentration in terms of grams per dm cube. That will give us 0.02155 grams. Okay. However, you need to, this is not the final answer yet, because this is the mass of potassium hydroxide that neutralizes the acids in 10 grams of oil. So the next part is somewhat like a mathematics problem. If 10 grams of oil requires 0.02155 grams of potassium hydroxide to neutralize the acid, then in 1 kg, which is 1000 grams, what is the mass of potassium hydroxide required? In this case, it will be 2.155 grams of potassium hydroxide.